Students, here in lesson number 2, we are going to be using matrices to solve systems of equations. To be honest with you, I would not say that this is the most efficient way of solving systems of equations. In fact, if I were to be truly honest with you, I think this would probably be the least efficient way of solving a system of equations, especially a smaller one like a 2 by 2 or a 3 by 3. Now, I remember doing this method when I was taking a class in college, and thinking along those lines, thinking, boy, this isn't a very efficient method. But then I was tasked with solving a 9-equation system with 9 variables, and that was going to be really tough to do by hand. And this method right here wound up being actually much more efficient. So, in reality, when we're practicing it here, we're going to do it on fairly smaller ones. But, I just do want to be honest with you that it would likely be faster to simply do it using substitution and elimination like we did in lesson number 1. All right. Specifically, the method that we're using is called the Gauss-Jordan method. All right, so most likely going to be a little bit of new vocabulary here for us. So first of all, we need to review what is a matrix. Well, a matrix is something that looks like this, and you've got numbers in it. 1, 0, 2, 3, 1, 5. And so these are rows, so like row 1, row 2, and these are columns. Column 1, column 2, column 3. We would say this was a 2 by 3 matrix. The rows come first, and then the columns. Each one of these individual places where there's a number, that's called a cell. These are the basics of a matrix that you need to know for today's lesson. We'll be learning more about matrices throughout the unit. The Gauss-Jordan method basically goes like this. You are going to take an augmented matrix. And so what is an augmented matrix? Well, let's say I had a system of equations like 2x plus 4y plus z equals 1, and 3x plus 2y minus 4z equals 5, and x plus y plus z equals 2. Well, what you would do here is you would just take all the coefficients, drop the variables, and just plug that into a matrix. So I'd say 2, 4, 1, and then 3, 2, negative 4, and 1, 1, 1. And for the Gauss-Jordan method, we're actually going to draw a little line here to indicate the difference between the equation part with the variables and the other parts. We'll say 1, 5, 2. And this is what is known as an augmented matrix. We've taken the coefficients and we have put them in a matrix. Well, the Gauss-Jordan method is we are going to use some matrix transformation rules to turn an augmented matrix into the identity matrix. So, what is the identity matrix? Well, an identity matrix can be any size, but it's always going to go diagonal with ones through just like this. So that would be the identity matrix for a 2 by 2 matrix. For a 3 by 3, which you will also see today, it would look like this. So if we can use some transformation rules to turn an augmented matrix into this, the results that we have right here are going to be our values for x, y, and z. All right. moving on. So what are some row transformations? Well, the row transformations go like this. Number one, you can change or interchange any two rows. So, row one, row two, you can flip them around. That one's not so bad. Two, you can multiply or divide through any row. This will be very important here in just a minute. Okay, so think of this as like the distributive property. Okay, you just take everything in the row and multiply or divide it by the same thing. And third, this one is kind of the more complex of the three. You can replace any row by the sum of the elements of that row and a multiple of another row. So what's going on here is, you remember when we had systems of equations and they're both in standard form, something like 2x plus 3y equals 4, and then maybe x minus 6y equals 2. And to solve this, we would multiply through this one by, say, -2. And then we would have these, then I'd have a 6y, -6y, and combine that with a -6y, and that would wind up eliminating something when I combine them together. That is exactly what's happening in this step right here. Row reduced echelon form, this is what we talked about earlier, the 1, 0, 0, 0, 1, 0, 0, 0, 1. That's what we're trying to get to. All right, let's go ahead and try just a little baby example. Step number one, we're going to just write the augmented matrix. So using my coefficients, I got 3, -4, and 5, 2. And then I'm going to write my answers over here. I guess 1, 19. And my goal is to get this into row reduced echelon form, the identity matrix, 1, 0, 0, 1. And so here's what we're going to do. We're going to use our properties, our row transformation properties that we just talked about. And I want to turn this number right here into 1. How could I turn that into 1? Well, I'm going to just, divide everything by 3 in that row. And when I do that, so the way that I write that, I'm just going to say 1/3 times row 1. That's how I kind of indicate my work. Well, 1/3 of 3 is 1, but then I'd have to take 1/3 of everything else. So that means I'd have -4/3 and 1/3 up here. And of course, row 2 stays the same. Okay, so I've got that. Well, now I'm going to want to turn this into 0. So I'm always I'm going to start by making that a 1, and then everything else in this row I want to turn into 0. And so how do I turn this into 0? Well, I'm going to use that third thing. I'm going to go ahead and multiply row 1 by -5. So -5 times row 1. Then I'm going to add that to row 2. So the top part, well, that's still just going to stay the same. So -4/3, 1/3, okay? But if I multiply the top by -5 and then add it to this, I get 0. That's what I wanted. But again, I'm going to have to kind of do all of this stuff here. And I've kind of pre-worked all the fraction stuff here ahead of time, so you can confirm everything. But if I take -4/3 times -5 and then add 2 or 6/3 to it, I wind up with 26/3. And then same process over here with the 1/3, I get 52/3. So you often wind up with awkward fractions here. Realistically, the problems we're giving you, you're going to get integer answers. So it all works out in the end, but in the middle of it, we kind of wind up with a lot of ugly fractions. All right, so moving on to the next step. Here we wind up with, well, now we want to turn this number right here into a 1. And so how do I turn 26/3 into 1? Well, I multiply it by 3/26. So 3/26 times row 2. And well, of course, 0 times 3/26 is still 0, so that's nice. And, well, multiplying it by 3/26 will turn this into 1. I still have 1, -4/3, and then 1/3 right here. Let's see, and then interestingly enough, 52/3 times 3/26 winds up just being 2. All right, well, the only piece I have left to figure out is this one right here. I need to get that into a 0. And so, how do I turn something into a 0? Well, I'm using the second property, the third property. So I'm going to take row 2, and I'm going to multiply it by +4/3. So 4/3 times row 2, and then I'm going to add that into row 1, and that's going to turn this into a 0. So bottom stays the same, 0, 1, 2. On the top, well, 4/3 times row 2, that's going to be 0 plus row 1, so that's why this stays 1, which is definitely necessary. But 4/3 times 1 plus 4/3 is going to wind up being 0. Yay. And then I got to do the same thing with the 1, so 1/3 times 4/3, 2 times 4/3, and then add that into the 1. Again, I just kind of pre-done all of this fraction work, but that winds up being 3. And so we've got this in row reduced echelon form. This is my x, this is my y, so 3, 2 is my final answer. And I'll bet right now you're thinking that the elimination method, not all that hard anymore.